Okay, in section 6.4, we're going to look at composition of relations. Now, this is really like composition of functions, but it can be a little bit more complicated because we know in functions there's like this unique mapping, and we do not have that situation in a relation, so this just can be a little bit trickier to find the composition of relations. So the composition of two relations is defined really basically similarly to how the composition of two functions is defined. So let's say we have two relations R and S on a set, and if we want to find the composition S of R, then it will be all the pairs AC if and only if there is a element B in the domain such that the edge AB is in the relation R and BC is in the relation S. So I think of B as being like the middleman. Okay, so we can get from A to B in R and then from B to C in S, and that would give us straight from A to C in the composition. Okay, so thinking of it in that like middleman, let's find for these, here's R, here's S, and then we want to find the composition of S composed with R. Now notice when I do S composed with R, I want to think about the edges from R first and the edges in S second. So I think if we can just systematically go through and say, all right, well, how could we use 1 as a middleman? Okay. So if 1 was a middleman, we want to first think of all the things coming into 1 in the graph, the digraph for R. Okay, well if we look at 1, it's only got edges going out. There's no edges in. Okay, and this is in R. And then if we look over in S, 1 goes out to 2 and 3 in S. Okay, but there's nothing coming in, so there's no middleman to connect things to vertices that were in R to things that were in S. Okay, so there's not going to be any edges that have 1 as a middleman. What about 2 as a middleman? Okay. Well, what's coming in to 2 in R? So 1 comes into 2, that's the only one. So 1 is coming in, and this is in R. And then we would have to go look at 2 in S. What's it going out to? Nothing. There's no edges coming out. Okay, so we can't use 2 as a middleman at all. What about 3? Okay, well, in R, we do have 1 coming into 3, and we have 2 coming into 3. So we've got 1 coming in, and we've got 2 coming in to 3. And then, this is in R. And if we look over in S, we want to look at the edges going out of 3. So out of 3, 3 goes out to 2, and 3 goes out to 4. Okay. And so the composition is we're just going to eliminate the middleman, and we're going to go straight from 1 to 2. So over here in our composition, we would go from 1 to 2. That would be an edge in our composition, and we could also get from 1 to 4 through the middleman of 3. So but 1 through to 4, 1 straight to 4 would be in our composition. Okay. And then we could get from 2 to 2, so there'll be a self loop there. And we could get from 2 to 4. So there will be an edge. So those are all the edges that we would get with 3 as the middleman. And what about 4 as our middleman? Well, coming into 4, we've got 1, 2, and 3 all coming into 4. And then coming out of 4 in S, so these are all in R. Okay, and then over in S, coming out of 4, we just have 1 edge that's coming out and going to 3. Okay, so if we eliminate the middleman, we can go straight from 1 to 3. So I'll put that edge in. I can go from 2 to 3, or from 3 to 3, so there'll be a self loop there. Okay. So this digraph would represent the composition S to R. Okay. So you know, the easiest way to get that composition, I think, is just to kind of methodically go through looking at all the possible middlemans and trying to see what edges will be in there. Okay, so that's the composition of functions. It's fairly straightforward. You just have to be methodical about going through the process of finding it. Okay, we mostly want to look at, in this video, section 6.5, which is about a special kind of relation called a partial order. So remember, we have a bunch of different properties that relations can have, and a partial order is a special relation that has 3 of the properties we've talked about. So a partial order is reflexive, antisymmetric, and transitive. So if it has those 3 properties, it's called a partial order. Okay, the canonical sort of partial order is less than or equal to. So if you think about less than or equal to on the set of integers, let's show really quickly that it's reflexive. So remember, a relation is reflexive if it's true that for all x in the set we're talking about, that is the set of integers, that x is related to itself. And since we're talking about the relation of less than or equal to, okay, so is this true that for every integer x, x is less than or equal to x? Well, because we have this equal to, yes, this is true. So it's reflexive. What about antisymmetric? Okay, so antisymmetric means that for every x and y, okay, as long as x isn't equal to y, that only one of x less than or equal to y or y less than or equal to x is true. Okay, so is that indeed the case? So if x isn't equal to y and I have 2 distinct integers, well, there's some relationship to them. Either x is less than or equal to y, or y is less than or equal to x. Well, we know they're not equal, right? And so only one of these, the only way that both of these could be true is if x and y were true, but we're only considering the case where they're not equal. So only one of these could possibly be true simultaneously. So, yes. Okay, so this one is antisymmetric. And then is it transitive? Okay, well, transitive would mean if I had 3 integers, x, y, and z, that if x was less than or equal to y and y was less than or equal to z, then it would have to be true that x is less than or equal to z. Okay, and yes, this is absolutely true. Okay, that's a property of integers, and so it is also transitive. Okay, so that's sort of the classic, very typical, when you want to think about what a partial order is, you're like, oh, it's like the less than or equal to relationship. And because that one is the most common and the one we think of most often, this notation, this is sort of curvy less than or equal to, is used to express the idea that 2 things, x and y, are related in a partial order. Okay, so that symbol there basically kind of reminds us that the relation acts like less than or equal to. And that helps us to trigger in our mind, oh, okay, this is a partial order, it's just like less than or equal to. Okay, so for example, let's say we had the domain, the positive integers, and we say that x is, and then instead of a capital R, so in previous sections we had x r y if x divides y. But notice, instead of putting an r here, we're putting this sort of curvy less than or equal to tell us that, okay, x is related in a partial order. Okay. So it's related by a partial order. So that special symbol there specifically tells us that it's a partial order. Okay. And we've seen before that this divides operation is reflexive because every integer divides itself. We've seen that it's anti-symmetric because if we have x and y that aren't equal, okay, either x divides y, or we could have y divides x, or that neither of them divides each other at all, okay, but we can never have that as long as x is not equal to y, we wouldn't get that both x divides y and y divides x. Okay, and then it's transitive, and we've seen that several times, that if x divides y and y divides z, then x divides z. Okay. So this is indeed it is reflexive, it is anti-symmetric, it is transitive, and so it is a partial order. Okay. So when we have a partial order, we can take the set A for which the partial order is defined, as well as the operation that is defining the partial order, and those two together is called a partially ordered set, or we abbreviate that as a poset. Okay. So for example, the set of natural numbers with less than or equal to is a partially ordered set, because when we take the natural numbers and use the operation less than or equal to, we get a reflexive anti-symmetric transitive relation. Okay, that will be a partially ordered set. If we take this set of positive integers with the divides relation, that's a partially ordered set. Okay. And so when we have a partially ordered set, two elements x and y are called comparable if either x is related to y or y is related to x. So there's some kind of relation. So if there is a relation between them, they're called comparable. Okay. If neither of these is true, so we can't find either of these, then they are called incomparable. Okay, so let's look at an example like this poset where we have the positive integers and the divides relation. Okay, so for example, if I picked the elements 2 and 4, okay, 2 is related to 4 since, okay, 2 divides 4. Okay. So these are comparable. So 2 and 4 are comparable. We also have examples of things that are incomparable. For example, like 2 doesn't divide 5, so 2 isn't comparable to 5. It's not, okay, I'll write this out since 2 doesn't divide 5. We also, like 5 isn't comparable to 2 either, since 5 doesn't divide 2. So 2 doesn't divide 5, 5 doesn't divide 2. There's no way to compare them. So 2 and 5 are incomparable. And that's why we call it a partially ordered set, because we don't have an ordering between every pair of elements. We only have part of them. The set is there's only an ordering relationship between part of the element, so it's only partially ordered. And that's in contrast to a totally ordered set in which every two elements that we pick are always comparable. We always have a way to compare them. So an example there is our set of integers and the less than or equal to. So no matter which elements I pick, I'm always going to be able to find a less than or equal to relationship between them. Okay. So 2 and 5, yeah, 2 is less than or equal to 5. 2 and 4, sure, 2 is less than or equal to 4. No matter which elements I pick, I'm always going to be able to put them into a less than or equal to relationship. And so, since every pair is comparable, that is called a total order. So, in partially ordered or totally ordered element sets, we're often interested in minimal and maximal elements. So a minimal element would be one in which there is no y, as long as it's not equal to x, where I can put y being ordered before x, y being related to x. Okay, so there is, if I was thinking about in terms of arrow diagrams, okay, I don't have any arrows coming into x apart from possibly x itself. And a maximal element there's no y that's listed after y. So if I'm thinking of digraphs, for example, I don't have any. I have arrows going out, but I don't have any arrows coming in. Okay, so let's look at examples so that you can see the idea here. So let's say that I've got this small. I don't want to do all of the integers because it can be tricky, but let's just do 2, 4, 8, 16, and 32. And we'll say that two elements are related. There'll be a relation from x to y if x divides y. And we want to show that it's a total order and give that it's minimal and maximal elements. Okay, so to show that it's a total order, we would need to show that there is always a relationship between every possible pair. So let's just go through them methodically. So are 2 and 4 related? Well, yes, 2 divides 4. So if I were to put 2 and 4 here, there would be an edge from 2 to 4. Is 2 related to 8? Well, yes, 2 divides 8. So I could put an edge from 2 to 8. Oh, I forgot 2 to itself. 2 divides itself. Okay, is 2 related to 16? Yes, 2 divides 16, so there's a relationship between 2 and 16. 2 and 32? Yes, 2 divides 32, so there's a relationship between 2 and 32. Okay, so 2 is related to everything. Okay, we already have 4 related to 2, but what about 4 related to itself? Yes, because 4 divides itself. Is 4 related to 8? Yes, because 4 divides 8. Is 4 related to 16 or comparable to 16? Yes, because 4 divides 16. So I could put this in. Is 4 comparable to 32? Yes, 4 divides 32. Okay, so that takes care of that. We have already done that 8 is comparable to 4 and 2, but is 8 comparable to itself? Yes, because 8 divides 8. Is 8 comparable to 16? Yes, 8 divides 16. Is 8 comparable to 32? Yes, 8 divides 32. Okay, so that's everything for 8. What about, is 16 comparable to 16? Yes, it divides itself. Is it comparable to 32? Yes, 16 divides 32. And now the only one we haven't considered with 32 is 32 comparable to itself? Yes, because 32 divides itself. Okay. So every possible pair of elements in there is comparable in some way. And so it is a total order. So every pair of elements is comparable. Okay, and then what about a minimal element or elements? Okay, so those would be all the ones that have only arrows coming out and no arrows coming in except for maybe when x is equal to y. So eliminate the self loops. Okay, so if I eliminate like the self loop here, I've got an arrow coming in and some coming out. So 4 isn't minimal. Okay, if I look at any of these, I've got some in, some out, some in, some out. Okay, but the only one that isn't like that is 2. If I eliminate the self loop, all I got is things coming out. So 2 is minimal. And if we look at maximal elements, okay, now this would be the case where we only have arrows coming in except for perhaps the self loop. And you can see here, if we eliminate the self loop, 32 only has arrows coming in and none coming out. So 32 would be an example of a maximal element. Okay. So this is an example of a total order. The minimal element is 2. It's comparable to everything, but nothing is, is less than it, or, in the whatever less than means for this particular, nothing divides it. Okay, and 32 is maximal because everything divides it, but it doesn't divide anything else. So let's look at different partial order examples. So we've got the power set of the set containing 0, 1, and 2, and the way that it's ordered is going to be with the subset relation. Okay, so if we look at the graph of this relation, we've got the empty set. Okay, and let's see, we've got the set containing just 0, we've got the set containing just 1, we've got the set containing just 2, we've got the set containing 0 and 1, the set containing 0 and 2, the set containing 1 and 2, and then we've got this set containing 0, 1, and 2. Okay, so if we were to look at the fact, so is the empty set, is it related to each of these sets? Well, yes, the empty set is a subset of every set, including itself, so it's a subset of itself, it's a subset of 1, it's a subset of 2, of 3. Okay, so every single one of these. Okay. So we already have relations between all of these sets and the empty set, but what about, is there a relationship between a set containing 0 and the set containing 1? No, this 0 is not a subset of 1, 1 is not a set of 0. These ones aren't related. Okay, but what is this a subset of? Well, it's a subset of the set that contains 0 and 1. It's a subset of the set that contains 0 and 2, and it's a subset of the entire set here. Okay. And then the subset containing 1, it isn't related to this 0 or to 2 because they aren't subsets of each other. What is it a subset of? It's a subset of the set that contains 0 and 1, and a subset that contains 1 and 2, as well as the entire set. 2 is a subset of 0 and 2, 1 and 2, and the entire set. Okay, now none of these are subsets of each other, but every single one of them is a subset of the entire set. Okay, so there would be a digraph for that. And now, are there minimal or maximal? Oh, and I forgot, we should put little self loops on all of these as well. Every set is a subset of itself. So of course we need little self loops. Okay. And so in terms of minimal elements, okay, that would have to be one where all of the arrows are going out and none coming in. Okay, so you can see all this stuff in the middle here has some stuff coming in, some stuff coming out, some stuff coming in, some stuff coming out. Okay, but this one over here, apart from the self loop, it only has things going out. So the empty set is a minimal element, and then a maximal element would be one that has only arrows coming in except for maybe the self loop. And so we can see over here, if we eliminate the self loop, only have arrows coming in, no arrows going out. So our maximal element would be the original set itself. Okay, now you can see that when we try to draw a digraph representation for a partial order, even with this small number of vertices in here, the number of edges can they're a little bit crazy, crossing each other. When you look at it, it's hard to kind of tell what's going on. And so we have something called a Hasse diagram because some guy with the last name of Hasse made this diagram, and so it's named after him. And it's used to depict a partial order on a finite set. And it shows all the precedence relationships by placing elements that are greater towards the top and elements that are smaller towards the bottom. And when we mean greater, we mean in this relationship. So we're talking about this being greater and this being, okay, smaller. Now that doesn't always mean greater, and this one doesn't always have to be less than this one and smaller, but we're saying greater in the sense that related by a partial order. Okay, the one that's in the position that you would think of as being greater if it was a less than or equal to. Okay, and what we're going, so there is, the position shows a relationship. So the higher it is, that means it has that means, so there's not going to be any directed edges, there's just going to be position. So lower things going up to higher things implies that there's an arrow going in that direction. So you can only go from bottom to top, you never go top to bottom, you only move bottom to top. And then we only include enough edges to make the relationships clear. So for example, we know that a partial order is reflexive, so we're not going to put any self loops in. Okay, it's clear to us. We know that that it's reflexive. There's no need to put them in there. We also know it's transitive, and so we know, for example, that because it's transitive, okay, if I've got an edge from the empty set to 1, and then I've got an edge from 1 to the entire set, by transitivity there's going to be an edge from the empty set to the major set. So really this edge here is kind of redundant, because I could just basically do a path that went from 0 to 1, and then so if I see that there's a path that goes there, then I know that that by transitivity that they're related. I don't need an extra edge in there. I can just look for a path. Okay. And so that is going to simplify and reduce the number of edges so that we can use a smaller diagram with far less edges, so that we can visually digest it much more quickly. Okay, so let's look at some examples. Let's look at how we would draw this same one. Here's the digraph version of it. How could I take that and convert it into a Hasse diagram? Okay, so we know that a minimal element is going to have to appear as low as possible. So anything that, so if we have two things that are related, x and y are related, x has to appear below y. Okay. So our minimal element of the empty set is going to have to appear on the bottom. Okay. And then we'll have edges going up from, so we have our set containing 0, we have our set containing 1, we have our set containing 2. And because the empty set is a subset of all of these, we're going to have upward edges. Notice there's no arrows, they're just going to be edges, okay, to show that these are related. And the way that they're related is that the empty set is a subset of the set containing 0. The empty set is a subset of the set containing 1, and so on and so forth. So when this is the greater set and this is the less set, the greater one will appear above. Okay. And then we also have the set containing 0 and 1, the set containing 0 and 2, the set containing 1 and 2. Okay. And now this is a subset of 0 and 1. And now, because there is an upward path going from the empty set through the middleman 0 up to 0, 1, I know that the empty set is also a subset of the set containing 0 and 1. But I'm not going to put that edge in there because I have this path. And so it's implied. And I don't add an extra edge because that just makes it too busy. Okay. And then I'm also going to have an edge from 0 to 0, 2. Okay. And now again, because there's an upward path from the empty set to set 0, 2, I know there's a subset relation there as well. Okay. And then as far as 1 goes, there's a subset relationship here and a subset relationship here. That's a 1. And then as far as the set containing 2, there's a relationship here and here. Okay. So If I want to know if two things are related, I just have to ask myself, is there an upward path between them? So for example, is there an upward path between 0 and 1? Well, I could go down and then up, but that's not an upward path. That uses a down edge and then an up edge, so no. Well, what if I went up first? So if I go up, well, then I'd have to go back down to get to 1. So 0, the set containing 0 and the set containing 1 are incomparable because there is no path that uses only upward edges. Okay, that's how I can tell the relationships, is it uses only upward edges. So 0 and the set containing 0, the set containing 1 are incomparable. The set containing 0, the set containing 2 are incomparable. The set containing 1 and 2 are incomparable because there's no upward path between any of those. Similar on this level right here, none of these are comparable because there's no upward path. I guess we would have to complete our diagram with 0, 1, and 2. Okay, so all of these are related. Okay, and now if I want to know, okay, well, is the set containing 1 related to the set containing 0, 1, 2? Well, as long as there's an upward path, then yes. Is there an upward path? Yes. Here's one. Here's another one. There's actually 2. Okay, is the set containing 0 related to 0, 1, 2? Well, yes, there's an upward path here, there's an upward path here, there's a couple different upward paths. So as long as I can find an upward path between two sets, then I know that they're comparable. Okay, but notice how this has far fewer edges. It has all the information that I need here. Every element is comparable itself automatically because it's a partial order. But we eliminate all of the transitive edges and we eliminate all the self edges and just have the important ones that can't be implied by anything else. And so this is much easier to look at quickly and digest than this kind of the whole entire diagram. Okay. Let's do this one as well. So this, here we had the whole entire diagram, which is kind of a mess. But if we looked at the Hassa diagram for that one, well, our minimal element would be 2. That would have to appear at the lowest level. And then 2 divides 4, so we would have an edge there. 4 divides 8, we'd have an edge there. Okay, and because there's an upward path from 2 to 8, we know that 2 divides 8. Then 8 divides 16, so that will have to appear at a higher level. And then because there's an upward path from 4 to 16, from 2 to 16, those are all implied. Because 16 divides 32, 32 would have to be at a higher level. And because we've got upward paths from 2 to 32, 4 to 2 to 32, 8 to 38, we know that those are all related as well. Okay. So in this one, we can easily see that this is a total order because there is a path, a straight path that goes from a minimal element to a maximal element that includes every element. Okay, so this, you can easily see this is a total order. And all of, if you compare that straight line path there to this with all the distractions, this is much easier to keep track of. Okay, and you can easily see this one is not a total order because we can't put everything in just a straight line. So this is easy to see that this is just a partial order, and this is a special kind of partial order called a total order in which every pair of elements is related. Okay. So let's look at some examples. Let's look at these various partially ordered sets and see, first of all, if we can find the minimal and maximal elements in each of them, and then determine if any of them are total orders. Okay, so for A, in here, at the lowest level down here, we've got D. Nothing's below D. Nothing's coming, there's no edges coming from a lower level into D. And so the minimal element here is D. And then for a maximal element or elements, okay, up here we've got A, where we've got things from lower levels coming in, but it's not going out to any higher level. So maximum is A. Now if we look at poset B, and we look for minimal elements there, there's a couple elements that have nothing coming in. So E It's got edges going out to higher levels, but nothing from a lower level coming in. So E is minimal, but F is in the same situation. It's got edges going up to higher levels, but no edges from lower levels coming in. So this one actually has two minimal elements, both E and F. And then looking at maximal elements, okay, you can probably see up here, A has something from a lower level coming in, but not going out to a higher level, so A is maximal, and B is in that same kind of situation. It's got an edge from a lower level coming in, but no edges out to higher levels, so B is also maximal. So we don't have to have, the minimum and maximal elements do not have to be unique. Okay, if we look over here at post set C to look for minimal elements, okay, now it's tempting to just go as far down and go, oh, H. Well, certainly H is a minimal element, okay, but notice that C has only edges to higher levels and nothing coming in. So C is also, now really we could have drawn C down here so that we could see that, but because, you know, to make all the edges, you know, everything that's one step away from B kind of at the same level, sometimes we'll just draw it this way. So D is this in a similar situation. So D goes up to E and up to F, but nothing coming in, so D is another minimal element. Okay, now really, you know, we could have drawn D and C down here at the same level as H, but we don't have to. So you just have to pay attention. And then the maximal elements, okay, A has nothing going to a higher level, F has nothing going to a higher level, so A and F are both maximum. And then over here in post set D, the minimal elements, E and D both have nothing from a lower level coming in. And as far as maximal, both A and B have nothing going out to higher levels. So those are the maximals. And then are any of these total orders? Okay, so total orders, like they're going to look like straight lines, right? So they're going to look like this, like a straight line. So it might be tempting to think that this is a total order because we've got a straight line here and a straight line here. But this is not a total order because in a total order, every pair of elements has to be comparable. And so notice that E and B aren't comparable, E and D aren't comparable, C and B aren't comparable. There's no relation between them. Okay, so even though we've got a couple of straight lines, it's not a single straight line. So are any of these? No, none of them look like a single straight line as the Hasse diagram. So none of these are total orders. Okay, so let's say we were given a digraph representation of a partial order and we wanted to find the Hasse diagram to kind of simplify it. So the first thing we want to do is eliminate all the self loops because we know every partial order is reflexive. That is implied. So I can get rid of these self loops. So I'll get rid of those. And then the other thing is we know that it's transitive, so any edge that's in there just because of it's transitive we can eliminate. So notice we have 1 to 2 and 2 to 4, and so we know there's going to be 1 to 4. So we could eliminate this 1 to 4. That's a transitive edge. We have 1 to 2 and 2 to 6, so we know we're going to have 1 to 6. We can eliminate that edge because it's transitive. Okay. But everything else that remains is important. So this, 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 this. These are all, none of those can be removed because none of them can be implied by transitivity or reflexivity. Okay, so if we were to draw this, we'd have 1 going up to 2 and going up to 3. And then at the next level, we'd have 2 going to 4 and to 6. And 3 going to 6. Okay, and so we can get, you know, all the things that we eliminated, like the fact that 1's related to 4 is in here because I've got an upward path from 1 to 4. The fact that 1 is related to 6 is in here because there's an upward path from 1 to 6. Okay. And so there are no other, like if I couldn't eliminate the 2 to 6, because if I eliminated that, there would be no upward path from 2 to 6. I wouldn't know it was related. Okay, I couldn't eliminate the 3 to 6, because then there would be no upward path from 3 to 6, and I wouldn't know that it was there. Okay, so this is the minimal number of edges that you can put in to determine all the relations. Okay, over in this one, we can eliminate all these self loops. Okay, and then in terms of transitive edges, notice I have A is related to B, B is related to D, so A is related to D, that's a transitive edge. I can get rid of those. Okay, everything that remains has to stay. Now we have to put minimal elements at a lower level. So notice A has only edges coming out and none coming in. Okay, just eliminate the ones in yellow and pink from your view. So A would have to be at the bottom. And then A is related to B and C. And then because B is related to D, D has to be at a higher level. So D would have to be up here. And we get all the relationships. Is A related to D? Well, yes, there's an upward path from A to D, so that relationship is captured in there. And then the last one here, we eliminate all the self loops. And then we eliminate all the transitive edges. Well, 1 is related to 2 and 2 to 3, so that 1 to 3 is a transitive edge. 1 is related to 3 and 3 is related to 4, so 1 is related to 4, that's a transitive edge. So all of these edges coming up here are transitive edges. The only thing that I need in my Hasse diagram is 1 going to 2, going to 3, going to 4. So that significantly simplifies it, and we can easily see that that one is a total order. All right, let's say that we were given the relation as a set of ordered pairs, and we wanted to draw the Hasse diagram. Okay, so this one is a little bit trickier, but once again, like we did before, okay, well, we know we don't need to put in any of the reflexive so this A to A, B to B, C to C, D to D, E to E, F to F, all of those, we don't need any edges in our Hasse diagram for that. And then we can also look for any edge that's in there because of transitivity. So B to E, is there E to something else? No. Okay, B to D, is there D to something else? Yes, D to F. So we have B to D, D to F, and so because it's transitive, we should have a B to F in there. We do. So this is a transitive edge. That's not going to have to show up in our Hasse diagram. And then we have C to A and A to F. And so by transitivity, we have to have C to F. There it is. That's a transitive edge. That's not going to have to show up in our diagram. Okay, I think we've considered every single edge now, and so the only ones that we're going to have to consider are the relationships that I haven't kind of circled to eliminate. Okay, so in terms of, so we've got B going out to E, B going out to D, but nothing comes into B. B is a minimal element, so B goes out to, well, I'll put D first since it's alphabetical, and then to D. So I'm taking care of those. And then we've got things coming out of C. So C goes out to A and C goes out to F. So let's do C goes out to A and C goes out to F. We also have this D to F. Let me draw that one in there first. Okay. All right, so we've got C to A here. We've got A to F. Oops, it was A to F. I think I put C to F instead. Sorry. Okay, so that's that one, and then D to F is that one. Not this. Sorry. I'll wipe that out for us. Okay, so get rid of this one. Okay, so pretend, yeah. So that's what yours should look like. Okay. All right, so there's our D to F. So we should have 1, 2, 3, 4, 5 in there, lines in there, 1, 2, 3, 4, 5 in there, and then all the rest of the relationships. So this B to F, there is an upward path from B to F. We've got that one in there. There's an upward path from C to F. We've got that one in there. And of course, all the self loops are implied. Okay, so that is what a Hasse diagram looks like, and much easier to quickly interpret than if we had included every single one of those edges.